So this is the first lecture in Chapter 1 of your Chemistry 151 course. In this chapter, we're going to be studying the very basics. I want you to also notate that on the syllabus, we do not go in order of the chapters, for example, 1, 2, 3, 4, 5. I skip around to teach it in a different order, so please pay very close attention to that. In this chapter, we're going to be talking about the study of chemistry, classification of matter, scientific properties, scientific method, significant figures, and basic formats on how to do conversions. When this is finished, I will upload practice worksheets in addition to the homeworks you have, specifically on conversion factors and converting metric system and densities, etc. They will not be for a grade, they are simply to help you. So when we talk about chemistry, our theme for this semester is going to be chemistry is everywhere. You eat chemistry, you drink chemistry, you wear chemistry, you are taking notes with chemistry, you drive chemistry, your refrigerator is doing chemistry. We're going to think about chemistry in terms of both, not a person, but a place, a thing, and a verb. And all of this is going to be encompassed and based on how we get to everything based on the scientific method. So if you've had any high school science at all, you have probably heard of and are familiar with the scientific method. So with the scientific method, we generally see it as a circular model where we start with observations, some sort of natural phenomena that we see happens, or maybe we just want to answer a question. So for example, why does milk curdle? Or why do we have to put milk in the refrigerator? For example, based on everyday life experiences, we know that if milk doesn't stay in a fridge or a cooled area in a refrigerator-like conditions, then it will go bad, it will turn. And we also know that longevity matters as well. So even if we keep it in a fridge, we can't keep it in a fridge for 6 months because then it will go bad as well. So if we wanted to note that and try to kind of answer that question, be able to. So we come up with some hypothesis. That's some sort of idea of what we think will happen. In high school and in middle school, you were told it was an educated guess, right? The hypothesis is this will do A because of B, for example. It's some idea that could be explained by some kind of process or thing we think we can do. So then we have our hypothesis. What do we think we can do to prove or disprove what we think is an educated guess? And by way of proving that or disproving it, we have to actually test it. We have to have our experiment. Once we have our experiment, we are going to collect data based on that experiment. It could be anything from observations that we see, colors, masses, weights, changes, etc. And we decide, okay, well, maybe we need to do further tests. Maybe we need to get a step further. And we continue and decide, well, once we have this testing going on, it did or didn't work, so let's revamp it and try it again in a different way. Not necessarily asking a different question, or maybe asking a different question, but getting down to the what did we see went wrong, therefore how are we going to make it correct or prove it or disprove it. With all of that said, what matters here are the states of matter. So what do I mean by that? States of matter are how a substance exists. We can have substances or a mixture of substances, and we can classify these substances as an element or a compound. Elements are the smallest unit and cannot be broken down any further without getting to an atomic level, which we're not talking about right now, but it's the basis. So a carbon can't break down into anything else. A chloride ion cannot break down into anything smaller or different. A compound is made up of these elements. So for example, sodium chloride, generic table salt, that's NaCl, it can be broken down into both sodium and chloride. It is a compound. When we talk about states of matter, we can talk about in terms of elements being just simply what we see on the periodic table. Your examples are, I've already said a few: oxygen, carbon, mercury, nitrogen. These are all just basic elements. It's the individual elements on the periodic table. Compounds are those elements. We can have all substances, theoretically, exist as a solid, a liquid, and a gas. Those are the three physical states. There are some that exist naturally in nature as a gas. Those are generically your nonmetals. Metals, generically, almost always occur in nature as a solid. And then the two liquids that occur naturally on the periodic table are mercury and the bromine gas. So that doesn't mean to say we can't melt gold or vaporize gold, which we know is a solid, or we can't take sodium, solid sodium, and melt it or vaporize it. It just means that theoretically any element can exist in the three different physical states. So states of matter, again, solid. What you'll notice with solid is that we have very packed, repeating geometric patterns here. Liquids, they get a bit more less rigid, more movement, less tightening, less repeating geometric patterns here. And then gases, these are no format at all, no geometric patterns, no stacking, none of that. And these particular properties are what directly lead to solid, liquid, and gases' abilities to maintain certain forms and behave in certain ways. So for example, if I have a square quartz rock, there's no way I'm going to be able to fit it through the top of this flask here. It's not going to fit because it's round, and my solid quartz is square, and it just is a cube, and it can't move or shift or change. It can't change its shape. It can't change its volume. Liquid will not really change its volume, but it can take the shape of any container it's in. Remember I said chemistry is everywhere? The characteristics of liquid being able to take the shape of any container is one of the biggest marketing tools for things like perfume companies. Think of all the fancy bottles that they put perfume in. That's a liquid. Things like soda companies like Pepsi and Coca-Cola. They have every year they come out with the glass bottles or the different shaped 20-ounce bottles or the cans. And you can easily recognize, if I put 3 glass bottles, empty glass bottles with no label in front of you, you would easily be able to distinguish out the Coca-Cola old school bottle that they bring back just about every winter. And that's a marketing tool based on the fact that liquids can take the shape of any container. Gases can change volumes, they can expand, they can contract, they can take the shape of any container, they can change directions, they only travel in straight lines, and they will only change directions when they hit a wall of the container or hit another gas molecule in the container. Now, gases will have the highest kinetic energy, meaning energy movement, and the lowest potential energy, where solids have the highest potential energy and the lowest kinetic energy. So again, elements cannot be separated into smaller, simpler substances by any kind of chemical means or physical means, so they just are. Compounds can be separated into different, words are hard today. Compounds can be separated out into their different elements. You can see here, I'm not sure exactly what this picture shows right here, but you can clearly see, based on the color coding, there are 2 different kinds of elements to make up this one compound. Perhaps this one in the middle is a carbon, and perhaps these 3 around it are oxygens. I don't know, but clearly the greens are one thing, one element. The purple is a different element, and then we could separate those out. Mixtures get a little bit different here. We have a couple of things going on. A mixture is simply that when we have two or more compounds or elements that are mixed together. What you can see here is that we have this, what we just saw, this compound we just saw on the previous page. We have this element here, and we have this element of elements and compounds. When we talk about mixtures, we can talk about them in terms of homogeneous or heterogeneous mixtures. What this means is, and this is how I always explain it, homogeneous mixtures means you can't really tell it's a mixture. So if I had a glass of water, pure water, a glass of salt water, and a glass of sugar water sitting in front of you, you would not be able to tell which one is which unless you tasted them. You can't see just by looking that there's two different things there. Heterogeneous mixtures, I kind of equate to vegetable soup. You can easily see that there's different things involved in the mixture. If you could pretend you could take your hand and pick it out and pick out the separate things, like pick out the carrots, pick out the celery, pick out the potatoes. If you could do that, you have a heterogeneous mixture. So when we classify this, you might want to go ahead and just, even if you don't print the slides out, go ahead and print this slide here just to have it as a handy reference for you. So you have matter, and depending on what kind of matter you have, you're either going to have mixtures or substances. Mixtures are made up of two or more different kind of substances and or elements, and they can be homogeneous or heterogeneous. Substances can either be compounds or elements. Elements make up compounds, and they can be separated from compound to element by chemical methods, where mixtures are separated by physical. Now, this particular table here, you have to memorize this. You're just going to have to know that what we're measuring, what it's called, and what its symbol is. And I want to take just a minute to emphasize something on this chart. Note here for the symbols that we have both lower and uppercase letters. In chemistry, that is critically important. What does that mean? Well, here's an example. And I'll do, that's it for now. Oh, and this one. Okay. These all look like M's. Some are uppercase, some are lowercase. You have four completely different abbreviations with these M's. This first one here, this first one is molarity. This second one is millimeters. This is molar mass, and this is meters. Much in the same way the capital and lowercase letters are important for abbreviation of different things, is the same way that I could say I have this or this. Capital C, capital O is carbon monoxide, where capital C, lowercase o is the element cobalt. Matters. Uppercase and lowercase matters. So here we're going to be measuring length in terms of meters, mass in terms of kilograms, electric current in terms of amperes, time in seconds, amount of a substance, that's going to be a mole, we'll learn about that later, and luminous intensity is the candela or CD. We won't do too much of this, but you will in Chem 2. So you need to know these symbols. And I'm going to be referring to these as kind of the parent unit, with the exception of kilogram, where although kilogram is the technical base SI unit, we're actually going to consider the parent unit of mass in terms of conversions to be grams. And you'll see why in just a minute. So this table, it is in your textbook. In your textbook, it looks a little bit different. I grabbed mine, this one that I put into the slideshow, I grabbed it from a different textbook that I have. I prefer this. Most of these tables I don't like because it leads students to believe things should be the number used for the conversion instead of them understanding it's the value of the unit. okay? So what do I mean by this? You are going to need to know this table. You have to memorize it. You have to know how to use it. You got to know it, all right? You need it for the test. When I look at this, I can say, all right, so if I'm looking at centi, and let's just say we're going to stick with meters for right now. 1 centimeter is this value right here, okay? So 1 centimeter is equal to the value of 0.01, or 1 times 10 to the minus 2. And it's actually going to be equal to meters. Why? For the same reason that 1 penny is equal to 1/100th of a dollar. The value of a penny is 1/100th. It takes 100 pennies to make up $1. So the way I want you to read this table is I want you to read it from left to right. And I want you to start here and think of this in terms of one of whatever the prefix is, centi, milli, micro, etc. One of these is equal to whatever number is here of the parent unit. Okay? So, for example, I could say, again, let's deal with meters. 1 micrometer is equal to 1 times 10 to the minus 6 meters. So 1 micrometer, that's a fancy Greek letter mu, you can see it down here, is equal to 1 times 10 to the minus 6 meters. Okay, I have a helpful information sheet on this with a short explanation below it that I will also upload when I'm done with this lecture. So mass is just a measure of the amount of stuff present, okay? Just the amount that's there. It's regardless of gravity. And this is why we can say an astronaut, for example, will weigh less on the moon than they do on the Earth. And that is because the gravity on the moon is less than that of the gravity on the Earth. So somebody's weight, how much do you weigh, is based on the mass that they have contained in them and gravity's effect on that. So if a man weighs 150 pounds on the Earth, in space, he might weigh 148 pounds or something like that. I don't know the exact math. But mass is just how much is there. So it's not that the astronaut has lost mass or being on the moon or the Earth. It's just that weight takes into account gravity. For temperature, there are 2 basic scales we're going to use. We're going to talk a little bit about Fahrenheit for the purposes of you practicing conversions, but I pretty much stick to Kelvin and Celsius. Kelvin and Celsius are the 2 temperatures we use. Celsius you've probably seen if you've had any high school science at all. It is read in degrees Celsius, just like Fahrenheit is read in degrees, F. And so you need to know that the freezing point of water is 0 degrees Celsius and the boiling point of water is 100 degrees Celsius. And Kelvin is absolute 0. Okay, it's an absolute temperature scale, meaning the lowest temperature possible ever in life is 0 Kelvin. Notice I did not say 0 degrees Kelvin. Kelvin doesn't use the term degree because it is the base unit. It is absolute 0. How do we convert from Celsius to Kelvin? Simply add 273.15 to the number of degrees Celsius. If you're given Kelvin and have to get to degrees Celsius, you simply subtract. I'm pretty sure this is going to be the easiest equation you have all semester. So here's an example. Normal human body temperature can range from 36 to 37 degrees Celsius early morning to the afternoon. Express these 2 temperatures and the range they span using the Kelvin scale. So if it is Kelvin equals degrees Celsius plus 273.15, we are simply going to take 36 and add it in. Yes, this is rounded. Please use the decimal in all calculations unless you're told otherwise not to. Adding them together, you get 309. Take the second one, plug it in, add it to 273.15, you get 310. For converting between Celsius and Fahrenheit, these are two different equations you need to know. One gets you from Fahrenheit to Celsius, and the other gets you from Celsius to Fahrenheit. You do need to memorize these, you need to know these, but you won't see them very often from me. You'll see them mostly on homework and the Learn Smart. So here's an example. I'm not going to go through this. It's just a matter of plugging and chugging. You can take time and go through it when you're. Here's your solution. Volume and density. We have a direct relationship between volume and density, and it has to do with mass. Now, for mass, you have to remember, we talk about density a lot, okay? We use the term density a lot, and often we use it incorrectly, okay? When you first move into an apartment or into a dorm room or into a new house, it's pretty empty. It's pretty sparse. There's not a lot of stuff per the amount of space you have available. But then once you live there for 5 years and you're like, oh gosh, it's time to move now, and you just have stuff everywhere. There's way more stuff for the space you have available. Well, kind of like that with leaves on the forest. You know, we've said, oh, this forest is very dense. When we say a forest is very dense, what we mean is there are lots of leaves and trees and bushes in a certain spot, hard to get through. Jungles are very dense, right? You know, you have to cut your way through just to walk through a path. Well, density in chemistry is basically the same thing. How many atoms are in a certain amount of space, where atoms is the mass and space is the volume. All right, time to redraw. I really don't know what just happened. Okay, if we know that, then we're going to say D equals M over V. We can simply just divide. Okay. 36 divided by 8. All right, so that equals 0.92 grams per cubic centimeter. Okay. Now, one thing I just want to notate here, this is why ice floats. You need to know that the density of water is 1.00 grams per milliliter. So the fact that the density is 0.92, that's less than 1, it makes sense that the less dense thing would float in the more dense thing. If it were 23 grams, go ahead and pause this and see if you can figure out the density at 23 grams. Same volume of ice. So that's D equals M over V. 23 grams divided by 8 cubic centimeters. That is equal to 2.875 grams per cubic centimeter. Okay, simple as that. So properties about all these compounds and elements we've been talking about have very specific properties, mainly chemical and physical. Physical properties that talk about physical change, that's where states of matter can change, but the essence of it doesn't. So for example, if I take a liquid water, let's start with ice. If I take ice and I melt it just by adding heat, and then I add more heat and vaporize it, the water molecules are still going to be the water molecules. They are not going to change, right? Because I can get those vapors back and I can re-liquefy it and refreeze it. It's still going to be water. That's a physical property and a physical change. However, chemical properties, this is when you can't get the original substance back. Okay, for example, if I have a car and the metal on that car rusts, there is nothing I can do to get that rust to turn back into the metal that was originally on the car. Now I can buff it off and paint over it, but that's not turning that rust back into metal. If I have a firework that explodes, there is nothing I can do to get that original firework back before it exploded. If I take wood and I burn it and set it on fire, there is nothing I can do to get that piece of wood back. Those are chemical properties based on chemical change. Some properties are extensive and some are intensive. And what that means is, does it amount, does it depend on the amount that is present or does it not? So anything that is extensive does matter the amount of something that is present, okay? Intensive properties does not depend on the amount of matter. So for example, mass, something that has a mass, that mass is the extensive property. But density and temperature, they're intensive properties. Density changes because it also is dependent upon volume, and temperature has absolutely nothing to do with mass. Well, it does, but for the purposes of what we're talking about, it doesn't. So this ends the first part of chapter 1. I'm going to do significant figures and calculations and accuracy and precision in a second part 2 upload that I will put up next. Okay, so make sure after you've watched this, maybe you need to go rewatch it, maybe you don't, and move on to the next one. Just keep going back and forth to these and using your book and maybe rereading your book after you've seen these lectures to see if there was any misnomers or something that didn't quite make sense that maybe now does. All right, see you soon.